All right, guys. So in this video, we're going over question 3 on the 2025 AP Chemistry exam for the free response questions that were released. So again, another thing to understand is, you might not have gotten this question. A lot of times they have different versions of the test, and they don't release every single question that some students were gotten. So if you didn't get this question, oh well. But and the other thing to remember is my students haven't taken the AP exam yet at West Springfield, so I might be talking to them about mistakes not to make. If you're watching this video and you took the AP exam on May 6th, then maybe you've already made that mistake and there's no going back, but that's okay. Hopefully you're here just to see if you got the right answers or not. So when we start with question 3, this is when, I remind my students all the time that they're going to throw a lot of different things at you on the AP Chemistry exam, but it really has to come down to, one of our 7 units or one of the 9 College Board units, right? So, I guess the buzz the day after the AP Chem exam were people complaining about a phosphorus pyramid and what's that. And I had my students come in and they said they heard on TikTok or whatever that, what the heck's the phosphorus pyramid? And, I didn't know what they were talking about. I hadn't seen the test or anything. And, I told them, hey, it's probably just a structure question or something. But I Googled the phosphorus pyramid just because I was curious, and it was some kind of like food pyramid about phosphorus traveling up the food chain. So nothing to do with this question. And so again, don't get intimidated when you see something that you're like, oh, I haven't seen that in my class. My teacher never told me that. I never did this. It's going to boil down to some key concepts, and that's it. And all you had to do here was recognize that phosphorus needs 8 valence electrons. Now, phosphorus can have an expanded octet, but it needs 8. And right now, each phosphorus only has 6 around it, right? A bond, a bond, a bond. Each bond is 2 electrons being shared. So we got 2, 4, 6 for that phosphorus, 2, 4, 6 for that phosphorus, 2, 4, 6 for that phosphorus, 2, 4, 6. Well, remember, phosphorus is a must-have 8, or it must have at least 8. So all I have to do is add a lone pair there, a lone pair there, a lone pair there, a lone pair there, and I'm probably done. But let's double check ourselves here, right? It's P4, right? There's 4 phosphoruses. So if we wanted to draw the dot structure for P4, the first step would be to know how many electrons, how many valence electrons, how many dots, how many electrons need to be represented in the diagram. So phosphorus has 5 valence electrons, and you have 4 phosphoruses. So, and it doesn't have a charge or anything. So 4 times 5, 20 electrons. If it was a -1, you would add another electron to it. Like if it was -3, you'd add 3 more electrons. If it was a positive ion, you would subtract that many electrons. But I have to have 20 electrons in my drawing because that's how many valence electrons each phosphorus atom is bringing to the table. So that's number 1. Right now, you count how many you have. Remember, a single bond is 2 electrons. So 2, 4, 6, 8, 10, 12. Right now, you have 12 electrons, so you're missing 8. Right? Remember, you're going to add them in as pairs. So you're missing 8, so you need to add 4 pairs. Well, you have 4 phosphoruses, so put 1 pair on each phosphorus, and you're golden. Okay? I think I have the drawing on the test. Yeah, so that's all you would need right here. Okay? And if you drew the lone pair here or the lone pair here, that's fine. But, and remember, phosphorus by itself, a lot of times when phosphorus is the central atom, many times it has 3 single bonds and 1 lone pair. Same thing with nitrogen, same thing with arsenic in that group, right? So, you're getting used to that trigonal pyramidal geometry. So again, if, kids making up an excuse like, oh, I never saw that before, I think it's just them understanding they probably didn't prepare well enough for the exam, and it's their kind of way to deal with things. And like, oh, I never saw that. It's like, yeah, but did you? The teacher can't possibly show you every possible question that you could possibly see, right? It's all about themes. It's all about concepts. It's all about that. And it's just like, oh, yeah, I'll add 2 more dots there, 2 more dots there, 2 more dots there, 2 more dots there. Now I have 20 dots in my structure, 20 electrons in my structure. I'm good to go. All right. All right. So, so 3 starts off with just drawing a dot structure. Okay. In part B, it turns into a thermodynamics question, right? So it's talking about thermodynamically favored. So understand what that means right off the bat, right? As soon as you see the reaction's thermodynamically favored at that temperature, that means the equilibrium constant is greater than 1 at that temperature. That means that delta G is negative at that temperature. That means if we were talking about cell potential, the potential of the reaction, the redox potential, the cell potential, it would be positive, right? So that statement tells me that right now, okay? It says the entropy change for the reaction, so delta S is negative. And we should be able to predict that just by looking at it. And that's essentially what we're trying to do is what confirms that delta S is negative? Why is there a decrease in entropy? Well, remember, basically, you have a solid and 5 gas particles on this side, and you only have 1 solid particle on this side, right? So you got 5 moles of gas going to 0 moles of gas. Remember, gases are way more entropic, meaning there's a lot more randomness, disorder, different states that the particles could be in the gas state. So that's more entropy. In the liquid state, they're less entropic, but in the solid state, they're even less entropic. So all the particles over here have made it to the solid state, very, very high order or not much disorder or randomness, not much entropy. So we have an overall decrease in entropy. But we got to explain it on the particle level reasoning. So let's see what I wrote here. So gas particles have much more entropy compared to solid particles due to their freedom of movement. The products are only solids, while the reactants have a solid and 5 particles of gas. The particles are becoming more ordered as the reaction proceeds, so less disordered. So therefore, it's a decrease in entropy. Okay. All right. And then it says the enthalpy change for the reaction is negative. Now, another way to ask this kind of same question is, because we already know that delta S is negative and the reaction is thermodynamically favored, delta H has to be negative. If you have a negative delta S and a positive delta H, the reaction can never be favored, no matter what the temperature. So anytime you have a negative delta S, the only time you could ever have a temperature for the reaction to be favored is if delta H is also negative. So they could also kind of not tell you the sign of delta H, but ask you to predict it based on the fact that it's thermodynamically favored and we already know what the sign of delta S is, okay? But this is one of those questions where are we agreeing or disagreeing with the student? And I think on every single agree or disagree question on this free response, it was always in agreement. The student was always right. We had a smart student taking this test, and we agreed with everything. That's not always the case. So, it's kind of, random here that every time they asked if we agreed or disagreed with, a student's conclusion, we agreed in this case, okay? So the student claims that favorability of the reaction is driven by enthalpy and not by entropy. And we should know that going in. A negative delta H is favored in terms of enthalpy. A positive delta S, or enthalpy, I think I said enthalpy. So a negative delta H is favored in terms of enthalpy. A positive delta S is favored in terms of entropy. So whenever you have a negative delta S and the reaction is favored, it's never favored because of the entropy change. Or when you have a positive delta, if you ever have a positive delta H and the reaction is favored, it's not favored because of enthalpy, okay? So we agree with the student. Enthalpy is driving the favorability of this reaction, not entropy. But we have to use the relationship between delta G, delta H, and delta S. And so, I think to go to this equation, and again, it's on your formula sheet. If we go to, if we go to thermodynamics, right, thermo and electro, right here, delta G equals delta H minus T delta S. Well, they're asking us to use those to justify it, and so here's an equation with all 3, okay? So that might be a good equation to reference, okay? And so remember, the more negative delta S becomes, the higher delta G becomes. And remember, delta G has to be negative in order to be favored. And the more negative the delta G, the more favored the reaction. So as delta G decreases, favorability increases. But the opposite is true. As delta G increases, favorability decreases. So they're saying the negative delta H is driving the favorability and not the negative delta S. And that's true. And it's because if you plug in more negative numbers for delta S, increasingly negative magnitude numbers for delta S, delta G increases. So favorability is decreasing as delta S becomes more negative. Okay, so the entropy change that's favored, that drives favorability, has to be a positive entropy change, and conversely, an enthalpy change that's favored is a negative, a release of energy, an exothermic process. Okay, all right. So we went from dot structure, so R unit 1, to thermodynamics, R unit 6. And then here we got, looks like calorimetry. So our unit 3 when we do calorimetry, okay? And this is the one when I was making the key, I had my first answers, and then I went back and I was thinking that maybe this was a question where they would test to make sure you have the right number of significant figures, but they don't say within the question. And usually if they're gonna ding you for significant figures, they remind you within that particular question to have sig fig. So I'm going to show you, my initial thoughts here, and then when I went back and said, wait, let's get the significant figures correct, even though we might not have to, let's go ahead and do it. All right. So we have this reaction. So the whole premise of this question is we want to use the calorimetry data to eventually calculate the delta H of this reaction. Okay. And so, right, you can see that here, we're going to calculate the delta H of the reaction through the calorimetry data. And the first thing you should just recognize is temperature went up. That means we have an exothermic process. So delta H, when I report it in part 2 here, should be negative. All right. Okay. So remember, the thermometer is measuring the temperature of the surroundings. So the temperature of the surroundings increased. That means the reaction, as the reaction proceeded, it was releasing energy to the surroundings. That's why it's exothermic. So if you saw that the final temperature was lower than the initial temperature, that's when you would say, oh, delta H is positive because it's an endothermic process because the reaction was absorbing energy from the surroundings. Okay, but here the temperature increased of the surroundings, so that means the reaction was releasing energy to the surroundings. Okay, and so part C number 1, we're just doing Q equals MC delta T, right? They give us a specific heat capacity. They give us the mass of the P4O10 that we added, and they gave us the mass of water, okay? So remember, water's density is 1 gram per milliliter, so 100 milliliters, 100 grams, right? And remember, when we do Q equals MCAT, we gotta, and we're mixing things together, right? It's not, we have 2 separate containers and it's just the heat being transferred, but we're adding this to that thing, and now we're kind of measuring the temperature of the solution. When we plug in mass for Q equals MCAT, it's got to be the mass of the entire solution. So the mass of the entire solution would be the mass of the water plus the mass of this. Now, that 0.1 isn't adding a lot of mass, but I guarantee you're not going to get credit if you just wrote 100 grams. You had to write 100.1 grams in your Q equals MCAT. The other thing to recognize is the question's asking for kilojoules, but specific heat capacity is normally in joules. So we're going to solve for Q, and that's going to be in joules, and we're going to have to divide by 1,000 to make it kilojoules. All right, so step 1, okay? So we plug in our mass, 100 plus 0.1, the heat capacity 4.18, and the delta T, final minus initial, and I get 159 joules. Now this is where significant figures might matter. When we do the subtraction, remember when we subtract it's about decimal places, and I didn't write it here, but it was 22.00 and 22.38. So when we subtract, we are limited by decimal places. So since they both have 2 decimal places, I'm allowed 2 decimal places. But when I do that, I get 0.38. Okay, so now the delta T only has 2 significant figures. So now when I do the math, technically, so I got 159 joules, okay? And if I divide by 1,000, that's 0.159 kilojoules. but I really should go to 0.16 kilojoules because I really should just have 2 sig digs. Now, they don't tell me I have to worry about sig figs in this particular question. You should always be mindful of sig digs. I don't think it's going to be a point penalty, but you never know. So, always be thinking about sig digs, just as long as it doesn't take a lot of time for you to think about, right? Okay, so the answer to part C1 is 0.16. Now, what matters about the negative sign is in the next part, when we actually reporting, this is just, how much heat was released by the reaction, okay? Or how much heat was absorbed by the solution as the reaction proceeded, right? And so we can have a positive value here. But when we're reporting the delta H for that process, for that reaction, we have to make sure we indicate whether it's endothermic or exothermic, and we know it's exothermic, and we indicate that with a negative delta H, right? So again, it's energy per mole. So what do we need to do? We need to divide by moles of a reactant or moles of a product produced, okay? Now, we got to be careful. We want moles per mole of the reaction. So if I figured per mole of water somehow, once I get that value, I have to multiply it by 6 to get mole of reaction. If I figured out per mole of this of phosphoric acid, I'd have to multiply it by 4 to get per mole of reaction, because this is showing 4 moles of phosphoric acid. But if I can get it per mole of P4O10, since its coefficient's 1, per mole of this would be per mole of reaction. And that's what we're going to do here, because we know how much P4O10 reacted. We know how many grams reacted, so we have to convert this to moles. Lucky for us, they gave us the molar mass. We don't have to worry about calculating it, which is not difficult, but they gave us the molar mass. So if I do 0.1 divided by the molar mass here, that's going to give me moles. And then all I have to do is take the energy value I calculated in part 1 and divide it by that many moles, and that'll give me energy per mole of the reaction, and that's my answer, as long as I have the right sign, as long as I made it negative, okay? So first, figure out how many moles of the P4O10, so grams divided by molar mass, and then take our energy value and divide it by the moles, and we get energy per mole. Now again, this is what I got initially, because I was using that answer with 3 sig digs, but later on, I was kind of, when I was going back over and double checking my work, I figured negative 450 kilojoules per mole would be the better answer if you want the right number of significant figures, okay? All right. So part D, now we move into Hess's law. So remember, we do this both in Unit 3 and Unit 6, but for delta H, we introduce it in Unit 3, in our Unit 3. So basically, we got to get this equation and this equation to add up to that. And that's part E. So before we go into part E, we have to answer this question. So kind of a lab error question. So the student noticed that not all the solid made it in to the water. So that means less of this reacted, so it would produce less heat. And that means the temperature change of the solution wouldn't be as high, right? So, so this is just asking, would the delta T be greater than, less than, or equal to the initial trial that we had? And we know it's going to be less than, because less heat is going to be produced, okay? Less than, the reaction would release energy, would release less energy, and therefore the solution would not absorb as much energy, so the temperature of the solution would not increase as much. So I should have the word less energy here. Yeah, okay. So less than, okay? And then here, so for our Hess's law, we got to get these two equations to add up to this, right? And understand, they might, kind of a tricky way to ask is they might not have told you that this was the delta H of formation of this. You might just, what's the delta H of this particular reaction? And then later on, they might ask, what is the molar heat of formation of PCl5? And remember, a reaction that shows 1 mole of a compound being produced from its elements is a delta H of formation reaction. So, okay, so, I'm just, for my students, maybe they tweak this a little bit. Maybe they use a similar question, but they tweak the way they ask it, okay? But really, you just need to, how do I get these equations to add up? So remember, if you reverse a reaction, you flip the sign of delta H. If you cut in reaction in half, cut it, divide it by 4, divide it by 5, divide it by 6. You do the same thing to the delta H value. And then once you get the two equations to add up to the overall equation, you just add up your new delta H's to get the delta H of that reaction, right? Okay, so the only thing I have to do is multiply this through by 1/4, because I need 1/4 P4, okay? And then if I do that, it'll end up with 1 PCl3, and then PCl3 would end up canceling, and it would end up with 3/2 Cl2 plus 1 Cl2, and that's how you get the 5/2 Cl2. So all you have to do is multiply this by 1/4, and then you add them up, and then you get your reaction here. So what you would have to do to this delta H value is divide by 4 or multiply by 1/4, okay? So here I multiplied that first equation through by 1/4, and this is what I have. And notice, instead of a negative 11 whatever, I have negative 287. And when you add the two equations, you get the equation you're looking for. So add these two delta H's, and you get the delta H of the overall reaction here, okay? All right, part F. So this is where I made an initial mistake because I miscounted, okay? So first we're gonna write we're gonna calculate Kp, okay, for the reaction. So they're telling us that this is a representative of the equilibrium mixture, okay? So at equilibrium, these are the particles. And they're saying each time you see a particle in this drawing, it counts as a partial pressure of 1 atmosphere. So if I see a particle once, it would have a partial pressure of 1. But if I see it twice, it would have a partial pressure of 2 atmospheres. If I see it 3 times, 3 atmospheres. And when I first counted, for some reason, I thought I saw 3 of these. And maybe I was including this one in the drawing. But what you would have to do is just count. So you got 1, 2, 3, 4, 5, 6. You have 6 Cl2s, so the partial pressure of Cl2 is 6 atmospheres. You have 1, 2, 3, you have 1, 2, 3, 4, be careful, 4 PCl5s, so 4 atmospheres. And you only have two PCl3s, so 2 atmospheres. When I originally did it, for some reason I thought there were 3 PCl3s, so I plugged in 3 for when I was solving for the Kp. All right. So, remember, the Kp expression would be Kp equals the partial pressure of the products divided by the partial pressure of the reactants. And remember, if they had a coefficient, you would have to raise it to the power of that coefficient. But all the coefficients are 1. But remember, like if this were a 2 in front of the PCl5, then it would be the partial pressure of PCl5 squared, okay? And then based on the drawing, plug in your numbers. And notice I initially had a 3 here. I've squeezed it in so I don't have to rewrite this whole page again. So the partial pressure of PCl5 was 4, it was 2 for the PCl3, and it was 6 for the PCl2, or for the Cl2, sorry. And so if you do your math, you get 0.333. When I had a 3 here, I got originally 0.222. That's incorrect, okay? So that is Kp. Now, you didn't have to write the expression, but it's good to write it out so you don't make a mistake when you're calculating, all right? All right, and then, sorry, the last part of question 3. Does the value of Kp increase, decrease, or remain the same? So remember, the equilibrium constant will only change if temperature changes. So temperature is changing, so we know it's not remain the same. Okay, so turn your 50-50, or turn your 1 and 3 shot to a 1 and 2 shot. So it's either increase or decrease. And just remember, exothermic reactions always become more favorable at lower temperatures. They become less favor at higher temperatures. So if temperature is increased for this, because this is an exothermic process, the Kp would decrease. The reaction would become less favored. And remember, a decrease in equilibrium constant means less favorable, okay? So Kp would decrease. So we would say Kp decreases as temperature increases. You probably want to say a little bit more than just because the reaction is exothermic, but you could say any exothermic process becomes less favored as temperature increases, okay? All right, so that's question 3. Come back to the next video for question 4.